In this video, we're going to look at end behavior models, how to find them, how to justify that we found them, and a little bit of how to use them. So first off, what are end behavior models? And in general, end behavior models are functions that behave like a given function as x approaches negative infinity or as x approaches positive infinity. Negative infinity being the left end behavior model, positive infinity being the right end behavior model. And the way we actually find it is the left end behavior model, I'm going to notate as b sub l of x, is the left end behavior model if the limit as x goes infinitely left, so x approaches negative infinity, of our function divided by the left end behavior model will equal 1. So in a ratio sense, they're approaching 1. They're approaching the identity. And similarly, b sub r of x, our right end behavior model, will be that if the limit as x approaches positive infinity of f of x over our right end behavior is equal to 1. And a few things to consider. So there's a lot of different types of functions, but I'll just put up 3 that we can compare. On the left, the thing that sort of grows the fastest would be an exponential function where, let me see how do I notate that, where b is, well, the magnitude of b is less than 1. Or another way to notate this would be b to the negative x. In this case, the magnitude of b is bigger than 1. And I'll explain this when we see our first example. So this has sort of top priority, growing the fastest out of the ones we can consider. After that, we have power functions with largest ends greater than 1 first. So x to the 4th will have sort of priority or take over for x to the 3rd. And the slowest growing to the left will be some log of negative x, so that I can actually have a function there, a value there. All right, so that's the order we're going to go for left end behaviors, is these specific exponentials, power functions, logarithmic functions. And it's very similar for right end behavior, except I need to have power functions where b is bigger than 1, or I can have sort of a b to the negative x where b, magnitude of b is less than 1. And then after that, I take x to the n, highest powers first, and after that, I take some logarithm of x. So this is just sort of a checklist. See if I have any exponentials that work on that end, then see if I have any power functions, then see if I have any logarithmic functions. There are many more functions that I could try to fit in, but this will cover what we need to see for now. So here's an example. Find the left and right end behavior models for this. On the left, this is the highest degree power function, and I have an exponential. But I'm going to write this down. As x is approaching negative infinity, 3 to the x approaches 0. It makes very little difference. The other two terms, x cubed approaches infinity, and negative 4x to the 4th approaches negative infinity. And so in here, I need to consider which one's going to take over, which one's going to make the biggest difference. And negative 4x to the fourth on the left makes the largest difference. It will grow negatively much faster than x cubed grows positively. So the left-hand behavior model of x will equal negative 4x to the fourth. Again, I have this exponential, but it's on the wrong side. To the left, 3 to the x is approaching 0, making very little difference. I want to see which makes the biggest difference to the function. And I'll consider, let's see what this looks like. So here is my original function. Here is the left end behavior. Let me make sure I put this correct. And I'm going to have to create a new function to show this. So I want to see that on the left, the ratio of the green to the red approaches 1. So let me create another function and make that be my function divided by my end behavior. And you'll see, okay, as I go further and further left, it does, sorry, zooming the wrong way, get closer and closer to 1. To the right it doesn't, so it's not the same on both sides, but to the left, the ratio of them gets close to 1. Alright, so let me clear this off a little bit. And that would be the justification for that. What about on the right? So let me switch colors. Well, on the right, as x approaches positive infinity, 3 to the x approaches infinity. And if a power function is growing, it will end up growing faster than, or sorry, if an exponential function is growing, it'll end up growing faster than any power function. So it's true that x cubed is approaching, sorry, this should be a negative here, is approaching infinity, and negative 4x to the fourth is approaching negative infinity, but exponential will grow faster. And just, if we start thinking this through, we start seeing what happens. So if I were to try to make an input-output table and consider 3 to the x and negative 4x to the fourth, well, when I put in 1, clearly 3 to the first is 3, negative 4 times 1 to the fourth is just negative 4, and they're about the same magnitude. If I put in 2, 3 squared is 9, but now 2 to the fourth is 16, times negative 4 is negative 64, and you can see close to 0, negative 4x to the fourth is much more important. But when we start considering looking at, let's say, 10, now 3 to the 10th means I'm multiplying 3 by itself 10 times, which will be a very large number, whereas 10 to the fourth, well, that's just 10,000. That's not too big. So eventually this will take over, and that means that the right end behavior model is going to be 3 to the x. And actually, let me write this in there. This is because the limit as x approaches infinity of f of x over 3 to the x equals 1. I can see that graphically. Let's go back here. And so here is that function. Now I see they're not necessarily close to each other, but they're going to both behave the same way. And you could see the green function started dropping low from that negative 4x to the fourth, but eventually it came shooting right back up. Let me sort of drag this in so you can even see what it looks like down there. So eventually it came shooting back up because the 3 to the x took over. And if I take the ratio of that, so that would be equal to my function divided by that end behavior, you'll see that it does end up approaching 1. I'll zoom in on that so you can actually see the 1. No, don't grab that. Alright. So you can see it does end up approaching 1. Now, one thing I want to stress before I go on is this. Just because the ratio approaches 1 does not mean that the functions are actually getting closer to each other. So if I tried to find the distance of f minus this right end behavior to see if they get closer and closer to the right, this is what happens. Let me zoom out in the y so we can actually see something useful. They started off close to each other, that's for sure. And it looks like they're getting closer to each other here, but it's not obvious. If I just found the distance from a point here to the closest point here, yeah, they are getting a little closer, but for a single x value, they're actually getting further apart. So let me turn this on, and you'll see that, okay, as I go farther right, f of x is much, much, much more negative than my right end behavior. Even though they look very similar and they do behave very similar, I can use them to do some limits, they aren't actually getting closer together. They just behave alike. Alright, let me fill in the rationale for this one, and then we'll go on to a use for this. So this is because the limit as x approaches negative infinity of f of x over that left end behavior will end up equaling 1. And I showed that graphically earlier. Okay, so why do we care? What's the use for this? Well, sometimes you might want to find these limits. Let me actually make that a positive infinity there. I meant to do that, sorry. Or I could just do this instead. I can cheat and get this color and just right over that. It was always positive infinity, I swear. That's a lie. Alright, so in here, I might not be able to just look at this and see what happens at negative infinity, but if I consider the left end behavior, in the numerator I have x squared and I have 2 to the negative x. As x is approaching negative infinity, this exponent is approaching positive infinity, so this will make the biggest difference at the top. In the denominator, I have an x squared, a 3x, and a negative 4. The x squared makes the biggest difference at the bottom, and so this limit will equal the limit as x approaches negative infinity of 2 to the negative x divided by 2x squared. And that was pretty easy, but I can't quite get the answer straight away by reducing, but it doesn't matter. If I look now, the numerator still grows faster than the denominator, so if I have a number that is vastly larger in the top than in the bottom, then this fraction will approach positive infinity. Positive because this will be going towards positive infinity and the squared will make this positive. If I had a vastly larger number over another number and one of them were negative, then this would be negative infinity. For the second one, I can look at the right end, and as x is approaching positive infinity, this term is approaching 0 because the exponent's approaching negative infinity. So x squared makes the biggest difference up there, but in the denominator, 2x squared still makes the biggest difference, which means that this will equal the limit as x approaches infinity of x squared over 2x, and in this case, 2x squared. In this case, the x squareds can actually reduce down, and what I'm left with is just the constant 1/2. A horizontal asymptote was actually going to happen. So let's look at this graphically. Going back here, getting rid of all of my graphs, making my graphs. Actually, let's see if I can do this. No, I can't do that. Okay, let me make this reasonable. Okay, and now turning on our new function, and to the left, we can see that it is going up towards infinity, positive infinity. It does a lot of stuff in the middle, and then to the right, it is approaching this horizontal line at 1/2. I hope that helped out. Feel free to comment below if you have any questions.